In this video, we're going to learn a shortcut for evaluating infinite limits of rational functions. So the idea is, we've seen that when we have a polynomial, the term that dominated the growth was the highest degree term, or the highest power term. So what we can do is we can ignore all the terms except the highest power term in the numerator and denominator. Because as we've seen before, and as I commented on at the beginning, the highest power term dominates. It dominates the growth, which means the highest power term grows so much more quickly than the other terms do, than the lower power terms. Okay, so let's do an example where we repeat all of the infinite limits that we did in the last video, but using this shortcut. So the first limit was the limit as x goes to negative infinity of this rational function. So if we use the shortcut says, okay, we got the limit as x approaches negative infinity, but only keep the highest power term on the top and on the bottom. So that's negative 4x squared on the top, it's 2x on the bottom, and this simplifies easily the limit as x approaches negative infinity, and we get negative 2x. And now we are actually good to plug in. It's negative 2, plugging in, we get negative infinity. Negative 2 times negative infinity, that is positive infinity. And if we compare this with what we got in the previous video for part A, notice that we also got positive infinity, but this is significantly shorter doing it the shortcut way. All right, so that doesn't mean that we can forget how to do it this original way. I do also want you to understand how this original method works. And on a homework, on a quiz, or on a test, I could definitely ask you to specifically do it using this original way rather than the shortcut way, because the original way actually sort of illustrates where the shortcut comes from. Because the only terms that ended up mattering in this original way were this term and this one, and those came from those highest power terms on the top and on the bottom. All right. Okay, so we were just doing this example. All right, so I want to make one general comment about this, which is, in general, if we are doing an infinite limit and the degree of the numerator is larger than the degree of the denominator, as it was here, then the limit is going to be either positive or negative infinity. The limit is going to be either positive or negative infinity. And we could use the shortcut to determine which one it's going to be, either if it's positive infinity or if it's going to be negative infinity. Conceptually, the reason why is, if the degree of the numerator is higher than the degree of the denominator, the numerator is going to grow a lot more quickly than the denominator will. So it'll end up being a really, really large thing, and what's left to determine is it a really large positive thing or a really large negative thing? So positive infinity or negative infinity. All right, so let's do our other two examples that we did in the previous video, but using the shortcut. All right, so example B was this one, this infinite limit. Okay, so I've already expanded out the denominator. Okay, so if we use the shortcut, we will get the limit as x approaches, this time it's positive infinity, and the highest power term on top is negative 4 squared, on the denominator is 16x squared. So we get negative 4x squared over 16x squared, and simplifying this, the x squareds cancel, and then I can divide the top and the bottom by 4 and get negative 1/4. And that's the same thing that we got doing it without the shortcut. All right, so that was really quick. So that's the power of this shortcut technique. Okay, so my comment about this is, when the degree of the numerator equals the degree of the denominator, then the limit is the ratio of what are called the leading coefficients. So the leading coefficients are the coefficients of the highest power terms. So if we look at those leading coefficients, the highest power term on the top is the negative 4x squared. So the leading coefficient is the negative 4. The highest power on the bottom is x squared, and its leading coefficient is 16. And if you take their ratio means divide them, we get negative 4 over 16, and that was our answer, because that became negative 1/4. So that's true when we have an infinite limit, either x going to infinity or negative infinity, and the degree of the numerator and the degree of the denominator are the same. Okay, so finally part C. Let's do part C as well. Okay, so for part C, I want you all to try this one. So pause the video for just a minute. It should be pretty quick because we're using the shortcut. And try this. So 4, 3, 2, 1, pause the video and try part C using the shortcut. Alright, so hopefully you've done that. Hopefully you've paused the video. If not, really go ahead and pause the video and seize this opportunity to practice this. So the shortcut says, well, we have our limit, and we keep the highest power term on top, which is negative 4x squared, and the highest power term on the bottom, which is 2x to the 5. Now I can simplify this a lot more easily. We get the limit as x goes to infinity. So negative 4 over 2 is negative 2. I can cancel some of these x's and be left with x cubed on the denominator. Now I can plug in and I'll get negative 2 over infinity cubed. So this is negative 2 over a huge number, negative 2 over infinity, which is going to be 0. It's going to get really, really small. And the general comment here is when the degree of the numerator is less than the degree of the denominator, then the limit will end up being 0. And conceptually, the reason why that is when the degree of the denominator is larger, if we have an infinite limit, that means the denominator is growing so much more quickly than the numerator will be. And that's what's going to cause the fraction to get really, really small and have the limit be 0. All right, so we've talked about how to find infinite limits of polynomials and rational functions rigorously in the last video, and in this video using a shortcut. And I want you to understand how to do it both ways. In the next video, we will talk about, well, how do we do other infinite limits? What about if I have to take an infinite limit of something that's not a rational function or not a polynomial? We'll do an example of that.